So welcome back to machine learning, and we're in the thick of things with machine learning now finally, instead of just math review. And I start with a couple announcements as usual. So first of all, some of you may have noticed that I post these lecture notes, but then during the lecture I end up making some changes, or then I find out that something is slightly wrong. So then what happens is I end up reposting the lecture notes with these updated versions. So just be aware that sometimes you'll have these lecture notes and then you'll notice that, oh, I cover something slightly differently. That's going to happen because it's kind of the first time going through things this way. So that's all I have to say. Unfortunately, there's no solution. Until I cover it, I then sometimes find little mistakes or things that I want to change. So that's all I can do. Also, I got these course feedback surveys, and I wanted to say the comments were very kind. It's very nice to read. I was quite happy to see that. So I appreciate that. Yeah, and then there was a couple feedback comments that I saw that were across many people that I will try to sort of, I guess, address. So the first one was there's this asking of more examples, maybe in the course notes or in general for practicing for midterms and stuff. And so I will do my best to do that, especially with these next few weeks being coding assignments. So then I'll try to, in the tutorial, and I'll add to the course notes some exercises and examples for things you might kind of see on the midterm. And then maybe before the midterm, I'll try to add some more to the course notes to practice. See what I can do. The second was this one about posting the course notes earlier, which I totally agree with you. I really wish I could post the course notes earlier, but the unfortunate truth is much of these are getting kind of generated at the fastest possible rate that I can. So I apologize that they kind of can't go any quicker, but I really wish I could have posted them earlier so you could read them and then come to class and stuff, but I do what I can. So that's the truth. And then the third one is there's actually a surprising amount of people that thought that the pace could be slightly increased, or that I didn't need to spend all this time kind of writing out a lot of things in class. And I partly agree with this. And so we will try this half pre-filled, this hybrid pre-filled in, I write the important parts. And I think this kind of makes sense because then I can spend more time maybe explaining and having more plots and examples at the cost of it being a little bit faster, but I don't know, we try. So we start from today, and then, I don't know, post on Piazza or something if you really have problems, and then we can talk about it. Okay, that's all the feedback. So let us continue where we left off. So we kind of ended at a nice point last time. Okay, so this was all this optimization business, and it was all just optimizing the estimate of the loss function. And we went over two main ways, which were this closed form solution and gradient descent. And the closed form solution was you just solve a system of equations. Gradient descent was you set the derivative to 0 and solve. Okay, and then this gradient descent thing gave us two kind of algorithms, one being this batch gradient descent, which essentially just did gradient descent, but with the function g being the whole, the estimate of the loss function using all of the data here. And then you iteratively apply gradient descent, and then you stop whenever you want. And by whenever you want, I mean after t epochs, and you output your weights, and then that gives you your predictor. Okay, the other algorithm was this mini batch gradient descent algorithm, which took more gradient steps, right? That was the benefit of it. It took more gradient steps to add another loop inside. However, each of the gradient steps were in some sense worse. They were less accurate kind of gradient steps. Why? Because now it's not the gradient of the whole loss estimate, but it's based on only some samples. So there's this trade-off if you take more gradient steps, but each of them is in some sense a worse gradient step. And it turns out that, in practice, there's some trade-off. Some cases it's better to make the batch size big. In some cases, it's better to make it small. You'll find that most of the time it's actually pretty good to make it small and trade off these being kind of worse gradient steps, but having much more steps that you can take. And that's what you see in the assignment, kind of, and that's what you should see. Okay, that's basically where we ended, and then we talked about yeah, you take more gradient steps, and then so on and so on. Okay, and then I added a plot here. So this is new stuff now, and I wanted to kind of show you what you're gonna what I guess you saw in the assignment, but we can now interpret the results live. And so you should see something like this, which is there's all sorts of different predictors we produce with these different algorithms. The first one being this closed form solution, right? So this is the closed form one where I called this output the W hat thing. This was from the closed form solution. And this was actually the actual minimizer of the expected or the estimated loss, right? So maybe yeah. So that was the actual minimize. It's the best fit line for this data. That's what that means. It best fits the data. And then gradient descent, like the visual interpretation, is that at the 0th iteration, you make a guess of the weights, which means you have some arbitrary line to start with in this 1D case. And so you might start with something like this, which is a pretty terrible, right, prediction of your, it's a pretty bad fit to your data. And then what happens is you do these gradient iterations, and we saw in terms of the loss function what happens, but in terms of fitting data, this is the story, which is that at the 5th iteration, so this is you've done 5 iterations, what you'll see is that the line starts getting closer to the best possible line. And then if you do 10 iterations, you get even closer. And in your assignment, you'll have this slider, which you'll see that if you get, if you take the number of epochs to be very large, you just exactly get the closed form solution. Okay. So that's how you can think of gradient descent. It's constantly getting a better and better fit as you increase the number of iterations. And in particular, it's a better fit to these data points that you have in your data set. Okay, that's kind of where we ended. And now, so far, we've only, okay, so this is where we get to the next thing, which is should we always use linear functions? All we've been talking about these linear function classes. And I mean, the answer is kind of obvious, which is probably not, because if the data doesn't look like a line, then you probably aren't going to fit it very well. And someone asked, is the only advantage of the for loops performance reasons or also consistent results? And I'm not entirely sure what that means, but yeah, there's essentially a trade-off of how many gradient steps you take, and it matters on a per case basis. So when we look at this extra loop, it's beneficial in some cases, and in some it's not as beneficial. That's really all you need to know. Okay. Yeah, so we had this question, which is, should we always use linear functions or not? And the answer is okay, so let's go into this. So the answer is going to be no. And when would you not want to use the linear functions? And it's going to be when your data doesn't look like it can be fit by a linear function, obviously. Okay, so we get into this topic called polynomial regression. Okay, instead of linear regression, now it's polynomial regression. And so what's going on? Well, let's look at an example. So assume you want to predict car prices based on age of a car. And this I thought was maybe a sort of realistic example, because you could think that the car, definitely car prices start high, then they decrease, as you can see from the data. But then maybe as they get older, they become kind of these antiques and whatever, and then they start slowly increasing again. So you might see some sort of a trend like this. And so if you try to fit this thing with a line, which is this red line that we have here on the right, you can see that the line might not fit the data so well. However, if you were to fit it with a quadratic function, like this parabola here, this purple, right, this purple guy, then you can see that this thing potentially fits the data better. Okay, so that's kind of the motivation for this polynomial stuff, is wouldn't it be great if we could use polynomial functions? And you can imagine if the data looks even weirder, maybe it looks like a cubic polynomial or some other trends, then you can use even higher order polynomials. So that's really the motivation. And then we talk about what precisely that looks like in terms of implementing that and whatever. That's kind of the rest of this optimization section. So what it really means is that this function f is now no longer the linear functions, but it's going to contain polynomial functions. Okay? That's all we're going to do. We're going to just make this thing bigger. And the way to do that is we do some examples to see how this might look for this what it would look like in this 1D case here. Okay, so first let's start with just the linear functions that we had. So this we've already seen. Here we have your feature dimension is d+1 because you account for the bias. And then here we're doing regression, so y is equal to r. And linear functions had this form. We said they look like this dot product, right? Where it was your feature dot producted with the weights. And when you apply the dot product, you end up with something like this. And in the one-dimensional case, you have a bias term plus the line, like the line part, the slope part. Okay, and the function class we said was just simply all of the functions, right, that are maps from features to labels, such that they looked of this form. That was our, and I'm going to add this one here now to this function class to think of this as these are polynomials of degree 1, right? So this is, there's no power of 2, power of 3, anything. This is degree 1. Okay. So you're going to see this trend now. So you can already imagine kind of what's going to happen for polynomials of degree 2. I'm going to add a term that has a squared in it. Okay. So that's the degree 2 polynomial. So now instead of the polynomial looking like this bias plus, or sorry, this function looking like a bias plus your weights multiplied by your feature, now your polynomial degree 2 is going to look like a bias plus this linear part, this line, like the slope part, plus a squared term. Okay, so this new part allows for us to have degree 2 polynomials. This is what like a degree 2 polynomial looks like. And notice, yeah, this is still the case where this d was 1. Okay. So now here's like a very important step to like maybe understand all of the polynomial regression thing, is that you can think of this function as a dot product again, however, with a transformed set of features. Okay. So just to go back, so in this linear function case, our features, we could think of it as being this like fixed 1 here, and then just a single feature x1. In the polynomial of degree 2 case, we can now think of this as just having new features, and the features are now not just x0 equal to 1 and x1, but we add a third feature, which is x1 squared. Okay, and this is like maybe the most important thing is like what we're going to think of like working with polynomials is we're going to think of just taking the original features and transforming them to have like these new kind of relationships between the original features. Okay, so in the above example, what would that look like? That would now mean we not only can have a weight that scales with age, but we can have a weight, like a parameter, kind of this w, and it would be this w2, that now multiplies not just x1, but x1 squared. So it multiplies the age squared. And so now that becomes very beneficial because now we can basically model this quadratic relationship. Okay. And so then this degree 2 polynomial function class is exactly like the degree 1 case, except now all that we have done is our functions are not just dot products of the normal features, but they're dot products of our transformed features. And we call this transformation, this phi. Okay, I guess I didn't write it here, but I wrote it later, but we call phi, so this guy here, this is going to be called a feature map. So it maps the features to some new set of features. That's not just transforms or maps the features. And the beautiful thing is that everything now looks the same as we have seen in linear, like in the linear regression setting, in the sense that it just looks like a dot product with some new set of features. So you could say it's a linear function in the new features phi. Okay. Notice this function class, once again, if you just think of this as the features, it looks exactly as everything before. This is going to be really important, as I mentioned in a little bit, which is you can just use everything we've learned so far, except now instead of working with the original features, you work with these transformed features. So the only step you need to do is to transform your features. Okay. Let's cover a couple, okay, one more thing to mention, which is quite important, which is notice that these linear functions, this class of linear functions, is a subset of all degree 2 polynomials. So the degree 1 polynomials are a subset of degree 2. This should make sense. If I just set this w2 to 0, then I get back the original like degree 1 polynomials. So in particular, this is a very important fact that we should keep in mind, that degree 2 polynomials just include more functions than before. Okay? So you strictly get more kind of power in terms of representing functions. Okay. And then I just give you the degree 3 polynomial case, which is, as you would expect, we can basically take the feature, this first dimension of the feature, to the power of 3, and then we get a new weight. to represent how that scales, and then everything stays the same, except now our feature map is phi3 instead of phi2, and it has a new kind of transformed feature index, this x1 to the power of 3. Okay, so different degrees cause for our feature maps, like these feature maps, to have different types of transformations. They include new types of features. Okay, and then the feature maps are just, all you do is change what feature map you use in there. Yeah, sorry, the function class f of 3 is just, the only thing that changes is what feature map gets used here. These will match. Okay, is there any questions about this? Because if this makes sense, then we're good. Yeah, so that's going to be the next example, basically. So I start slow with the case where the dimension is 1, just to get an idea of like how you're introducing just a squared and a cubed and whatever term. And then we're going to talk about the case in a second where we add, where d is larger than 1. Yeah. That's right. Mm-hmm. Yeah, so the question was kind of like, how does this relate to the example in some sense? And like here I'm saying that the relationship is as you square the age, maybe, then you notice that the price kind of scales as the squared, well, a shifted version of the squared age. If instead, and I suppose I will erase something, but instead imagine the data had some sort of like relationship maybe like this, then you might have like a cubic relationship that you will need to model, and so on. And in general, the data, and we'll see some pictures. Oh, there, this is good. And we'll see some pictures later on of if the data has just like some complex relationship, you can model it by some more complicated looking polynomial, basically. That's what it allows you to do. And if needed, these function classes, like as you add more polynomials, they always have the ability to just be lines or be like quadratics or be cubic things. So you don't lose the like the ability to represent lines or polynomial like quadratics or cubics. You only gain new functions that you can use. And so you can already start seeing like why don't, like we'll talk about it in a second, but like why don't we just make it the polynomial power as large as you can possibly make it? Because then you can just represent everything you could ever want. And we'll talk about that. But before we get there, let's continue the story. Sorry. So yeah, this allows you to represent more complex, like to better fit more complex data, kind of. Okay. And this, once again, is a very important relationship that you should remember, or you should like, I mean, you can clearly see it. That this is only the linear functions. These are the polynomials of degree 2 or less, right? They can always be lines as well. And this is the polynomials of degree 3 or less, which can obviously always be a polynomial of degree 2, and so on. Okay, so it just includes only more, like strictly more functions than before. Okay, so now we consider the case that was kind of asked about. What happens if d equals to something larger than 1, like d equals 2? How does this kind of like relationship look like? And so I just give it through an example, and then I give you the general case right after this example. So here, all that's changed is d equals 2. So now we are working in R3. In particular, in this linear function case that we've seen already, this will just look like, the features look like this, right? X0 is, this is X0, always equal to 1. And there's X1 and X2. And you take the dot product with the weights. And so it just looked like this kind of relationship. But now there's two different types of like kind of features in X1 and X2. Okay, and then the linear function class was just this, the functions that looked of this form, everything we've seen so far. Now what's going to change is for the polynomial of degree 2, we're going to need to kind of consider every possible combination of feature multiplied with each other. Okay. So yeah, let's look at this. So degree 2 polynomials now becomes more complicated. So we still have this part, which is the linear part, as before. But now we add in the like degree 2 part. And the degree 2 part, what you have to do is you have to consider every possible pair, because it's to the power of 2. So every possible pair of features. In this case, it would be x1 times x1. You would consider x2 times x2. And then you would consider x1 times x2. You can imagine if you had like x1, x2, x3, you'd have much more combinations. You'd have like x1 times x1, x2 times x2. Then you would have like x3 times x3. And then you would have like x1 times x2, x1 times x3, x2 times x3. So there's all these different combinations. And yeah, they give you all of these like kind of quadratic relationships between features. So yeah, but the important thing is that this kind of gets all captured in the feature map. So this phi2, depending on the dimension of its input, is going to map you to these like degree 2 polynomial features. So now you can think of this as simply being a dot product with some new weights, right? These weights are now in a higher dimension, but the features have these new like added transformed features in some sense. Okay, so that's how it looks in general for larger Ds. And then your function class, once again, is as we've seen above, everything's the same. You just change the features to these transformed features. So the important thing to understand is how we're transforming features, which is through this phi map. Afterwards, everything is basically the same story. Okay, so now I give you the general story, which is the following story. And let me see if I missed anything. Yeah. So in general, we're going to have this thing called phi of p, which is a feature map for degree p polynomials. Okay, this is like the main new thing. There's just this thing that transforms features. Everything else basically the same story. Now the thing that's of interest is like, what is the dimension of these new transformed features? Because we saw above that now the dimension, like originally we had these things that were in R3, but now somehow it became R6 because we had to consider all of these like combinations of things. And you can imagine if D is larger and P is larger, like the degree of the polynomial is larger, then this is going to get larger and larger. And it turns out to have some like slightly complicated formula that I don't want to get into the details of why it is this formula, but I give you like, but here's the formula. So if you start with your features in this dimension, so R to the D plus 1, which is what we've seen, then the new features, right? So look at this feature map. This feature map takes the original features and maps to some new feature dimension, like some new space. This Z is going to be R to this P bar. Okay, so this is going to be a higher dimension. And we'll recover the previous examples in a second. And this P bar is going to be this equation. It's going to be this like combinatorial kind of equation, which is D plus P, right? D is the original degree of the features, or the original dimension. P is the degree of the polynomial. And so it's D plus P, choose P. And yes, for the sake of time and stuff, I'm not going to go over why this is the equation for it. Maybe we go over it in the tutorial for fun. But the point is that this is the equation, and as P grows or D grows, then this thing gets larger and larger. Okay? That's what you need to know. So we can now use this formula to see if it matches what we've seen before. So let's look at the example where D was 2 in the above case, and P was 2, right? So that was up here. D was 2, and the degree was 2. So that was what we call P. What did we have here? We had R to the 6, right? That was just looking at, we have like x0, x1, x2, and then these other new guys. So we have 6 of them. So we look at the formula, and we're told that P bar is going to be equal to this 2 plus 2 choose 2, or 4 choose 2. So if you calculate that, it turns out to be 6, which matches what we had above. Great. Okay, but what this allows you to also do is now you can like see that for higher degrees, how many like features do you end up getting? And so if this is an example we didn't do, which is if D equals 2, but the degree of the polynomials is now 3, right? We haven't done this example. We can just quickly see that using this formula, we would have 10 features. So we started with technically like D plus 1. So we started with like 3 features, and then we end up with 10 features. And so as you increase the degree of the polynomial, you're going to get much more features because you're going to be considering all these different relationships between the features. That's the main story. And then the function class in general becomes this f subscript p, where p denotes the feature map's degree, like the degree of the polynomial feature map you're using. That's it. So everything goes through this feature map thing. Okay, and then you have this relationship we've already seen, which is like every time you increase the degree of the polynomials, you just get a bigger and bigger class of like predictor functions and whatever. That should all make sense. Okay, so I give like one side note is like here we have a very fixed, we have a fixed feature map, right? So we've this in the sense that for a specific set of features, we map it in a very specific way, which is to polynomials. I just want to mention that like this is almost becoming like the neural network business, except all that happens in neural networks is you don't have this phi being like some fixed function that we decide on beforehand, but it gets learned. So that's, I just add maybe one note is like, you can think of neural networks as learning some feature representation. So they take your original like data, they map it to some representation, and then at the end, they just multiply it by some set of parameters. This is like some very nice way to think about it. And all that's happening is they're just learning how to represent the data in some nice, good way. And here we're like kind of hand tuning and choosing, okay, like if we transform it in this polynomial way, maybe it gives us the relationships we want. Yes, no, okay, maybe it works, but yeah. Okay, that's just like one note. So the beauty about all this is, as I said, like everything looks like we've seen before. Everything is just this dot product. All we have to do is just basically we just need to implement this phi function as an algorithm. Like if we can take in some feature and output the corresponding feature, like the corresponding new features, the transform features, we're done. We can just use everything we've seen before. So in particular, you can solve for this like new W hat P using the closed form solution, let's say. So that just becomes this, yeah. So you can solve for this thing as before by just minimizing L hat, this estimate of our loss. And the only thing that has changed is that L hat now has this little subscript P to denote that we're not working with just any linear functions. We're working with linear functions based on this transform set of features. So notice how everything basically looks like the same thing. This thing is the only thing that's changed. So you can like literally in your assignment, you will have like these closed form solution learner, you will have this gradient descent learner, and you can just reuse those exact same functions with the data being this transformed data, being this transformed set of features. So all you're going to have to do in the assignment is implement phi. And then once you've implemented phi, you just pass it into all the previous learner functions you've implemented, and it just does the learn. Like it's just that easy. Okay, so yeah, you can run the closed form solutions. You can run gradient descent just as before. And for the sake of time, like in the course notes, I give pseudocode on how to implement this phi. I'm not going to talk about it in the class, but you can see the story. It's not too complicated. You just you take the features and then you try all the different combinations. So you try x1 times x1, then you try x2 times x2, then you try x1 times x2, and so on. There's just like a couple loops that you have to do. It's pretty straightforward. And you implement this in the assignment too. Okay, and here's something you should know because all of these function classes become richer or bigger than the other, right? They're going to have functions that potentially can fit the data better. And how you would see that is that you would see that the estimate of the loss, right, for the best weight vector returned by using the degree 1 polynomials. Okay, so this one denotes, like this one here, and this one denotes that we're using phi of 1 here. This is the original like linear functions case that we've been doing. So what you'll find is that this has the highest estimated loss. If we move to degree 2 polynomials, the estimated loss becomes smaller, and so on up to degree P. So as you make their functions, in some sense, contain like more interesting or richer functions, so this function class gets bigger, then your estimated loss gets smaller and smaller. Okay. So this is kind of like the big takeaway of what is the result of all this. Function class gets bigger, estimated loss always gets smaller, or at least not larger than before. Okay, very, very important. And I show this by a plot. Well, this is kind of the last plot to end this optimization stuff, which is now we have some weird, so these black points are just some like, maybe you have 5 data points for some reason. And yeah, so you have 5 data points and you plot it. And now the question is like, how do you best fit the data? And we can try fitting the data using different function classes. So first we start with the function class that only has linear functions. That's this orange one, and it fits it with a line. And this is what we've been doing for most of the optimization stuff. So the best line fit might be something like this orange function here. Then if we increase the functions to, say, these polynomials, you're going to get something that fits the data maybe a little bit better. This green thing kind of looks like it might fit it better. And as you increase p to be very large, what you're going to get is some very complicated looking polynomial like this purple one. And it's essentially going to fit the data almost perfectly. It goes through like all the points. And your estimated loss, I guess I should write this. So this thing is going to eventually become approximately 0. You're just going to fit the data perfectly. Okay. That is like really a very important takeaway. And so the question we end the optimization chapter and kind of jump into the next one with is, why not set p, right? P, like the degree of the polynomials you're using, as large as possible. Okay, so this is like a very important kind of takeaway to have after all this optimization stuff. We did all this optimization on our estimate of the loss, L hat, right? And we said, okay, like, yeah, this estimate's going to change if we change the function we use in here, of course. But as we increase like the function class, this estimate's going to get, we can make it smaller and smaller. And like, why not just make it 0, right? Like, why not get it to 0? Yeah, that's what this question is asking, and we address this in the next notes I'm going to get to. But maybe before, as I'm transitioning, does anyone have like an idea of why don't we just make p as large as possible? Sure.
Because if, for example, you have data points that like take up a big range, but no kind of class, they'll just plot like this, basically, through all of them, and actually be accurate with the detail you get the points.
But what's wrong with just fitting, like, even if you have this, what's wrong with just like fitting it in this very complicated way? Like, like you can still, if you want to fit the data, didn't you like fit the data really well then? Maybe I take your.
So overfit our data, and if you have to like make things different, you'll have to
Yeah, so that's basically the answer. And that's essentially what we're going to spend a lot more detail than you might ever suspect in the next lecture or two talking about exactly what this means. But the answer is something like, if you fit this data really well, if you ever see any new data, which is not exactly these 5 points, so suppose the actual true data, and maybe I plot this, imagine with a new set of points, let's say blue ones. So imagine like the actual trend of the true data, and I can never like draw all the possible points, but I draw like a lot of the possible points. And we're going to do this again in a second. But like maybe it actually looks something like this. And this was just like one outlier out there. Well, then what you'll see is that this thing is quite bad at predicting these points and these and these. And yeah, some of these are better, but yeah, so on. So on new points, this thing might not be so good at predicting the labels. And kind of our goal, I'm going to cover in a second, is like we at a high level is like we want to be able to predict, right, labels well for like any possible input. Like so, like you get some new whatever information about something, a new feature, you want to be able to predict that correctly. Okay, so let's talk about that. So we go into what is now called evaluating our models, or evaluating our predictors / models, right? This is really what happened is like we would output this predictor, right? And as the polynomial degree got higher and higher, we would output a predictor that better and better fit the data. But at the end of the day, did we actually output a good predictor? It's kind of what we're going to try to answer. Okay, and let me just make sure I don't miss anything. Yeah, so the question is, okay, so did we actually output a good prediction stuff? And before like maybe jumping into exactly what our objective was with outputting a good prediction stuff, I want to ask like a question based on the stuff we were just doing before, which is, you might remember in ERM, we had this claim, which was that L hat, right, of our output, and I'm going to put this F hat, and I'm going to put a little D here for a second, and I'll explain it. But you can see this is like, so F hat is like the output of our algorithm, and we said that this estimated loss of this is, okay, so I asked this question, which is like, is this thing really, is it really a good, wow, really a good estimate of L, the true expected loss of this predictor? Okay, so this is like a very key question that if we understand the answer to, it'll turn out to kind of be able to really make everything else a lot easier afterwards. So I guess like really make sure this part makes sense. So right, like this whole ERM thing would work great if the thing we outputted, like this L hat thing, right? This is the thing we actually end up, like we end up outputting this. We actually output this predictor, and why did we output it? It's because its estimated loss was really small, right? We were getting this thing closer and closer to 0 as we made p larger and larger. But it would be good if at the end of the day, it actually was a good estimate of the true thing we cared about, which is like the true expected loss. Okay. And so the answer is going to be that it's like it depends. And it depends on some things. And the things that it depends on are very important to understand. Okay. So this is our setting. And in particular, just remember, like, we have this learning algorithm, it outputs a predictor. And I'm going to subscript this predictor with a data set D. Okay? And here we're going to think of the data now in terms of like this evaluating our model and stuff as a random variable. So we're going to think about like, how does our predictor change if the data changes? And we'll see this in a moment too. And I just remind you of some terms, which is this L hat thing, right? This was, okay, maybe before telling that, like this is the true thing we actually want to make small. It's the expected loss, right? So it has this expected value, and you want to make this thing small, and this is based on data that's coming from the true distribution over like whatever your features and labels are. So you have this data coming from this true distribution, you want to make its expected loss small. Okay, so this is the thing we want to know. But the thing we have is this estimate of it, which is just like this sample mean estimate, uses n data points. And yeah, it's a sample mean estimate of like this predictor's loss. Okay, so these are the two terms we're kind of working with. And now to answer this question, I go on a slight detour on like working with like, I just give you like maybe a little thought experiment, which is first, so yeah, forget about this question slightly. Maybe I write like, slightly forget about this for 1 second, which is, okay, consider this case, which is that if we, imagine we picked some function from here. So like we picked a function from our function class. And then after that, we gather data, right? And in particular, like the way you would say this in statistics is you've chosen f, like your predictor, independently of the data set. Of course, we're not doing this, but like imagine you do this, right? So you pick a function, and then you gather data. Okay, so what does that look like? That looks like you picked an f. So I chose some f. I know like for no reason, I don't know. So for some reason, or like I just choose an f with kind of like no context. And then after that, let me gather some data. So I gather like this data set and I plot. Okay. Like doing this should make you like feel like in some sense comfortable that this kind of makes sense. So you pick a function, then you gather data, and then you can ask, what is like how well did my function fit that data? Because like, yeah, like the data was gathered after the function was picked. Okay, so in particular, okay, there's like some details, but all you need to remember is that we had this thing which said that the expected value of our estimated loss equals to the actual expected loss of that function. Okay, we had this thing which is like, yeah, as a result. And I just want to, like, we worked through these steps in the estimation chapter, but what I want to highlight is there was one important detail for this to work. And that important detail was there was like this equality step here, and this one required that all of these things in the sum were all identically distributed. Okay? And this is actually completely fine, and it works out in this case because I just chose some function. It didn't depend on data or anything. And we knew all of these xi and yi's were all independent IID of each other. So these turn out to all be identically distributed. Everything's fine. This function is just completely independent of the data. And then the other important thing that we also covered was that the variance of this guy, the estimate of the loss, is equal to 1 over n times the variance of the loss of any one of these data points. In particular, the key takeaway was that as n gets larger, the variance of our estimate gets closer, like it reduces. So it becomes like, it basically varies less and less. So it becomes closer and closer to its true expected value. And the important thing here was that we needed another crucial assumption to make things work, which is that these things were independent of each other. Okay. All that being said is that, what am I trying to point out here? It's that if you pick a function and you gather data, estimating how good the function fits the data is totally fine by using that data you gathered. Because first you pick the function, then you gather data, and the data didn't depend on the function in any way. Okay. This will hopefully seem much more obvious why I'm really emphasizing this, like you pick function, then pick data thing. In this next, like basically the kind of the opposite of this, which is like what we're doing, which is like we're doing this. So we're not picking a function and then gathering data. What we're doing is okay, so I just write what's happening. We are gathering data, right? So we gather D first, and then based on the data set, we then pick our function. So we then pick this f hat of D that's an element of this function class. Okay, so this is like pretty, like one of the most maybe important things. And in other words, what it's saying is that this f hat, the function we pick, depends on the data set. Okay, and this is like a big red flag in statistics that anyone would have ever learned, but here's what it looks like. It's like you have some data, right? So that we start with gathering data now, instead of picking the function first. And now we look at the data and we decide to pick our f hat based on the data. And then we hope that, like the claim we were kind of making before is like, now we think that, oh, the estimate of the loss of this thing is actually a good estimate. Well, like, how could that be? You know, like in some sense, like if I specifically chose this function to perfectly fit the data, how can I expect this thing to be like a good estimate of what the true expected loss is? Like, what the true expected loss is you would like try to like think of like what does all the possible data, like what does the actual distribution of data look like? So maybe I can plot what maybe the true data, like if I were to get more points, maybe they look like this, right? Maybe they actually all look like this, so they follow some sort of thing like this. And if we looked at our estimate of the loss, what we would see with these 5 data points and this red function we picked is we would find that our estimate of the loss is 0. However, clearly, this red function does not perfectly fit new data. Like the true expected loss is definitely not 0, this thing. Okay. So there is this crucial thing, which is that if you pick a function based on data, right, it might not be such a great estimate. Okay. In particular, there's going to be like some mathematical expressions that you actually don't need to work out, but they highlight some very important things of like what changes how good of an estimate it is going to be. Okay, so in particular, if we just try to work out the same steps as before, so if we just try to calculate this expected value of this, what you'll find is that you can no longer apply this like equality step here, which required things to be identically distributed. And the variance formula, what you're going to find is you also can't apply this step here, which required things to be independent. Okay, so there's going to be these two things. You're going to need these these things to be independent and identically distributed. And the story is that if you look at what is this thing, like this loss function of f hat and whatever, you're going to find that it's not IID. Like, why is it not IID? It's because, look, the predictor depends on the data, right? So like this thing completely depends on the xi's and the yi's you chose. So you no longer have like n IID samples of whatever this thing is. You now have something that itself depends on data. Okay. And so it turns out that you can no longer kind of like use all these things that we saw before that gave us all this intuition about whether our estimates were good or not. And these are like, I just give you kind of the formulas, but they give you some insights as to what is really the story, and these insights should kind of make sense, I hope. Which is, first of all, you'll find that this loss, this like estimate of our loss, it's actually in general smaller than the true loss. And we kind of saw this in the plot, right? This red thing, if you were to calculate its loss on these data points, it's much smaller than what the true loss would be from the actual like data distribution if you were to gather it. Okay, so first of all, it's not even like the expected value isn't quite true. But maybe the more important thing is that the variance here of this thing no longer is just 1 over n times the variance of a single like one of the losses. It's now 1 over n times some more complicated stuff. And I want to talk about the more complicated stuff in a little more detail because it gives you kind of like one of the most maybe important properties when we talk about how to choose between the degrees of the polynomials or the complexity of the function class and so on. Okay, so here is the important thing to note. Notice that the variance, so how much your like loss estimate is going to change with different data sets, depends on the maximum in your function class, the maximum variance of this. In particular, okay, as the function class gets larger, the thing you want to note is that the variance of your estimate is going to get larger. Okay, and this is like more formally kind of the problem with picking a really high degree polynomial. So when you pick a really high degree polynomial, your function class gets a lot bigger, right? And if that gets a lot bigger, it turns out your estimate actually gets worse. So in other words, what this is saying, and this is really the key takeaway, is that this estimate of our predictor, right, becomes worse as f gets larger or as f becomes what people usually say is more complex. Okay. So you pick like a larger or more complex function class, you end up with estimates of the true loss being worse and worse. Okay. Oh, maybe I should. Whoa. What is it? What am I writing here? Let me rewrite this. Becomes a worse estimate of this true loss of this guy. Okay. So this is like really the crucial takeaway of all this. Increase the function class, you get a worse estimate of the true expected loss. Okay. So that's what happened in the polynomial thing, is like, yes, this estimate of the loss gets smaller and smaller and smaller, but at the cost that we were actually not modeling this true expected thing we actually cared about. Okay. And we're going to see some plots, and this all comes up in these like trade-offs of how you pick these things very, very soon. Okay, so the story is, okay, so that's about the function class. Okay, so that tells you something about like the function class, like what size function class should you pick. And then there's one more like important variable that's like talked about in machine learning about what you should pick for it, which is, I mean, it turns out there's always one best choice kind of, and it's like, if you look at the size of the data set, you still see that the variance decreases with it as before. And so as n gets larger, this variance goes down. Okay, so as we gather more data, our estimate gets better. So in other words, these are the two kind of opposing factors, which is this, our estimate of the loss becomes a better estimate. Okay. So increasing data makes the estimate better, but increasing the function class makes the estimate worse. Okay. But why would you like still just like remember, like why would we want to increase the function class? Well, it's because we can actually make like this thing, if it still is a good estimate, then we can make this thing still quite small. So there's going to be this trade-off where making the function class bigger and bigger, this estimate gets smaller and smaller. But then there's going to be a point where that estimate is no longer actually modeling the true thing we care about. Okay, that's going to be kind of like the whole rest of the things we try to talk about now, which is this trade-off of the two things. Picking the complexity of the function class. Yeah. Right. So yeah, so we're trying to decide something like, we have data, right? So I'm just basically kind of re-explaining things is what the question was. So we have data here, right? And the problem that we might be kind of like visually seeing is that if we pick our estimate, f hat, which is what we're doing, to minimize the loss, which in some sense is saying fit the data as best as possible. So that's what this red thing is doing. Right? That's how we're picking this f hat. It's like this argmin of this estimated loss. And what is the estimated loss? It's just like a sum of how close you are to each data point. So this might be a function you output. But the thing we actually care about at the end of the day is producing something that has a good, like a small expected loss. And so you might ask then, like, is this thing, so the thing we actually make small is this. This is the thing we make small. F hat is chosen to be the thing that makes L hat the smallest. If you remember, like, yeah, I can write this. So usually this like F hat thing is chosen to be something like the argmin in whatever your function class is. Of what? Of this estimated thing. So this thing is literally the minimizer of this function. But then we ask, okay, like that's all wonderful, right? Especially because like that's all wonderful if it actually is a good estimate of this. So like there's kind of this one step, which is like the thing we want to make small is this, which is how well we fit on any, like all future data. And that can be kind of thought of as this purple stuff. Like this is like maybe, clearly this is not enough data points, but like this kind of represents all possible future data. And we want to ask like, how well does it fit on all future data? And we can say that, oh, it will fit well on all future data if this estimate is close to this, right? So if these two are close, and we'll actually see this a little bit more rigorously in a second, but like if this estimate is actually close to this, then we can expect it to fit well on future data because we've literally chosen this guy to be the smallest, the function that makes this the smallest. So all that was kind of missing. Like we did all this optimization. We always just assumed this was a good estimate. All that was kind of missing to like tie us back to reality was whether this truly was a good estimate. In ERM, there was this first step of estimation. Was this really a good estimate? Like if it was, we'd be okay. And now I'm telling you that like it depends. Like it's not always a good estimate. This L hat thing, like the quality of how good it estimates L actually depends on some things. And what it depends on is how much data you have and how big your function class is. So if you're picking functions from a very complex function class, like this is a very complex function. This would be like, I don't know, polynomials of degree T10 or something. Then what you'll find is that this might not be a very good estimate of the true expected loss. But if instead you're picking functions from like a smaller function class, and to take the extreme other case, imagine your function class literally contains one function f. Well, if you only have one function to pick from, then of course this is a good estimate of it. Like, you gather some data, or like you can think of it both ways then. You can think you gather data and then you chose your single function from the function class. If you have almost no choice of functions, then you can't really fit that function to the data. So as your function class gets bigger, in some sense, you have like options of way more functions to pick from. And if you have way more functions to pick from, you can make the function really fit the data like super precisely. And that causes this problem of then you're probably not going to be estimating the true loss correctly. It's this thing called overfitting. And yeah, maybe the next stuff will make this slightly more clear. But all that I was trying to emphasize was that essentially this thing that we always thought was a good estimate, we should reconsider. Like, not maybe reconsider, but we should note that it is a function of two things. The size of the function class is n. And these are going to be the two parameters we kind of plot and talk about a lot now. Okay. And I just quickly see if there's anything. Yeah, I think I already answered some of these questions. Yeah, I think I already answered all the questions on there. So let's move on to what was like another way to kind of look at this stuff and like our kind of goal objective and whatnot. So let us remember what was kind of our goal from this. This is the supervised learning stuff. Okay, so what we did so far in the class is we talked about what supervised learning is. We then said this was our goal. We then talked about how ERM can be one approach to try to achieve the goal. So then we talked about how to make like how to implement ERM. But what we haven't talked about is, did it achieve our goal? And this is what I was trying to like, I was just right now jumping at like these two steps of ERM. Yeah, well, maybe let me remind you, ERM, all it did was it estimated, like it used this L hat thing to be an estimate of L, and then it picked the argument. And we just asked, do those two steps kind of like make sense and whatever? Okay, so here is the objective, right? This is the objective we had from supervised learning. It was we wanted to define a learner such that the expected loss was small on average over the data sets. So like, you don't know what data set you're going to get. You want this to be small regardless of the data set you're going to see. In particular, if we kind of like look back at this plot, what you could think of is like, if you got a different 5 points, right? Not these 5 points. I draw a different 5 points. If I got these 5 points, would this red line still be a good estimate? It's maybe okay, but like it's far worse than it was on the black points, right? So you can see as the data set changes, the thing that your learner outputs can be like quite different in terms of its actual like loss. Okay, so to understand like where, so there's this objective we have, and we're going to talk about this thing, but to understand how to think about this objective, kind of the conventional way to do this, and okay, I'm going to do it in a slightly unconventional thing, and then we'll talk about this, we'll talk about it in a more conventional way soon. And I really think this is better, so we'll see. Maybe I'm wrong, but we're going to go down this path. So, but both of the stories have, like, I'll explain where it's unconventional in a second, but both of them have the same idea, which is like, you try to think about where does the error come from in like, okay, so you have this term, and like, it turns out there's various things that cause you to have errors or for you to not achieve this objective well. And so the idea is to talk about those various aspects of the error. Okay. So that's what we're going to do. We're going to like break this down into different parts, like different errors, and we're going to see how each one can be made smaller or larger and how each one interacts with one another. So we're going to write this thing as like a sum of a bunch of error terms. But to get there, we need to first define some things, and then we can write it. Okay. So we start with a very simple case, which is, suppose that the learner didn't, like, instead of using a data set, the learner had more power. Suppose that the learner, suppose that this learner A actually just knew the true distribution of X and Y. Okay. What would it do? Like, if it knew this thing, it didn't need to like do any estimation, none of this business. It would just like, it would really pick the function that minimized this, right? It wouldn't try to use any data, like, it doesn't need data. So what would it pick? Okay. And so here, this is kind of like the best thing we could, okay. Like, what's the idea? It's the idea is that like, this is the best thing we could ever hope for the learner to pick, which is it would pick the function in the set of all possible functions. So I'm not even restricting the functions we can pick from here. So these are all possible functions from x to y, right? So this, and it would pick the thing that minimizes the true expected loss. Okay. So this is what are like, if we had all this information, this is what we would pick. And it turns out this is a useful thing to compare to. And so we're going to give it a name. So this predictor is going to be called, it has like actually a special name. It's called the Bayes optimal predictor. So we denote it by this F Bayes thing. Okay, and this thing has a special name, which is called the Bayes optimal predictor. So this is like, if you knew the actual distribution things were coming from, and you had no restriction on the functions you would pick, you would just pick the best function, right? So this, in some sense, is the best thing we could ever hope for our learner to output. Okay. So let's imagine what that might be. Maybe it looks something like this, right? So this is an example of what the function might look like, right? What does this depend on? This depends on what the data distribution looks like. So this is kind of saying that like as x is increasing, right, it has this kind of trend. I don't know what kind of variable might have this trend, but like, I don't know, maybe it's like the number of rooms. For some reason, the number of rooms, it has like, the true trend is that it increases and then somehow it drops because people don't want houses with too many rooms, but then it starts increasing again or something. Okay. So this is like the true kind of fit to the actual house prices or whatever. Okay. And even this thing, here's the thing I wanted to mention, is that even this thing is still not going to have 0 expected loss, potentially. Why? Because you can imagine for some like number of rooms, you still might have the case that like, okay, maybe on average, like things really are, maybe they really are like around this point. But what you'll find is that like, this is the average, like you're measuring the average loss, right? So you're measuring the average of how close this value is that you're predicting relative to every data point. So what you'll find is that, yeah, something like this. Like maybe this is number of rooms is 2. What you'll find is like you can have various prices still around those number of rooms, right? But this thing just predicts the best thing on average. So like, yeah, so I just want to mention that this is somehow like this error that is still potentially not going to be 0 because for a specific like number of rooms, you still might have various prices, right? Houses are not always going to be the same price for some number of rooms. And we'll talk about how to, like what this error is called and how to make it smaller momentarily. But I just wanted to point out this is like one type of predictor. It's kind of like the best predictor we could hope for. Then we can kind of reduce the amount of information, or like we could reduce the information that the learner has, or like what the learner has the ability to do. And we could see, okay, like what would it do then? Or like what's the best it can do then? And the next kind of natural way to reduce things is tell it, okay, this learner cannot just map to any function, right? It has to be a function in some like constrained function class. So like, for instance, let's say it was all linear functions. We still give the learner this ability to know the true distribution of data, but it can only pick the best linear function. So what would that look like? So then the learner, and so now you're going to see why I've reserved a special kind of like symbol for a while now. So what the learner would do is pick the best function in the function class, and here I just chose an F1 for the example, that minimizes the true expected loss. So we're trying to get to this point of like what the learner actually has and like all these different like things that it would ideally do. Okay. And this thing, we're going to give it a name, and this is now finally going to be not F hat, but F star. Okay, so this is where the star is reserved, and the F star denotes the best possible predictor, but based on this true expected loss. Okay, what does that look like? Well, that might look something like this. It's like knowing the true distribution, this is like actually the best possible line that could fit it. Okay, notice how there's some discrepancy here, like F star is not F Bayes. Why? Because you couldn't pick the best possible function, because your function class doesn't have the best possible function. Okay, this is going to be we're going to talk about the error between these two things. This is what I mean about like we're breaking things up into errors. And so we're going to also talk about how to like reduce these errors and what changes these things. But you can already see like what's kind of the cause of this. It's like this function class was restricted. Okay, and now we can move on to really the case that the learner experiences. Like what is the learner really dealing with? And the learner is dealing with like the case that it doesn't know this. Okay. It doesn't know the true distribution the data is coming from, right? But what it does know is it has a data set, and that data set is actually sampled according to this. Okay. And so this is the case we have. We have a data set instead of this actual true distribution, and we have a learner that we usually restrict the function class, and we'll see why we would want to restrict it. It's going to be way more clear why we've been doing this restriction in a second as well. So yeah, so then what is it? What do things look like? Okay, well, first of all, what is our learner? Our learner then becomes what we've like. Unsurprisingly, our learner is actually like what you would expect here, which is like f hat. This is the thing we've always been talking about, and this is the argument predictor in the function class. But remember, we don't have access to the true expected loss. Now we had to deal with this like kind of estimate of the expected loss. Okay, notice how there's some discrepancy here. We had this L hat because we had to use data, while here we had the true expected loss. This, of course, will be good if L hat is close to L. Notice how now I had this discussion earlier about, is L hat close to L? Okay. So in particular, what this might look like is now we don't actually have the true distribution, we have data. So we have these 5 data points. And now at f hat might be something like this. So now notice, not only are we restricted to linear functions, which is much weaker than what f base was restricted to, but also we don't even have the true distribution, so we have to fit to this data. So now we have some error in f hat relative to f star as well. Okay. And I want to, okay, so there's this kind of, there's really these 3 kind of errors we're going to talk about in a very short moment. But visually, this is how they should look like. Okay. Yeah. Right. So it totally depends on what the like underlying. So the question is, why is f star not equal to f base? And we're like, it can be under like depending on basically what you pick here. Okay. So if I make this thing, for instance, all the functions, then it will equal f base. Okay. So, but here I've restricted it, and I've restricted it for a reason, because we're going to talk about how changing this affects the different errors. So you can see here, if I made, and we're going to talk exactly about this, which is if I make this bigger, right? If this, let's say, is like cubic functions, what you might find is that, oh, I can actually fit this pretty well, right? But then what you're going to find in the next plot is that now f star relative to f hat is quite, is like what happens is f star and f hat become further apart. So there's going to be this trade-off between the 2 things. And yeah, so that's exactly what we're going to talk about. Yeah, like f star can be f base if you make the function class large enough. It's a very important intuition that we'll emphasize a lot again. Okay, so there's another question to ask here, which is like, so far I've talked about a very specific data set here, right? I wrote it as 5 data points. A thing to consider is like, what happens if the data set changes? Like, how does our predictor behave? And so I draw it maybe for a different data set D2. And so, okay, maybe these are like some really weird data points, right? I've only got them around this area now. And even then you can see, okay, the line is different, but like, and okay, so clearly our predictor is going to change if the data set changes. But one thing to kind of note is maybe it's not too different. Okay, like it's different, but it's not like unbelievably different. And this is going to be in contrast to something I show in just a moment, right? So like, thing to note here is that data set changing, you get different predictors. Okay. So now let's consider if the function class changes to f2. So this is kind of like addressing maybe in part the question that was asked, and also how data sets change. So now the function class is f2. So I can now use polynomials of degree 2 and lower. So I could always use the line if I still wanted to, but now I can also use polynomials of degree 2. F star now changes. It's now going to be the best function that's in this class of polynomials of degree 2 or less. That fits that minimizes the true expected loss. Maybe that looks something like this green curve. Okay. Notice how it's different now. And the argument is that it's getting closer. Okay, it's getting closer to the true f base. Okay, we're going to make this even bigger in a second. But the argument is that f star is getting closer to f base now. Okay. Now the other thing that's changing is that obviously our estimates are going to change too, because now we can use like polynomials to fit, or quadratic functions to fit the data. So f hat changes, right? It changes to this thing that maybe now better fits these orange points. And maybe the purple ones you still like, there was no need to really change to a quadratic function, so you still pick a line, like it still would pick a line because that really turns out to be the best fit. So notice how we are not in any way restricting ourselves to not pick lines. So this is just strictly more powerful. Okay, but now the claim, there's like kind of two things, is that f star is now getting closer to f base. But there's an argument that f hat and so this f hat based on one data set and this f hat based on a different data set are now going to start varying quite a lot from each other. Okay? So yeah, you change the data set, the thing you output is going to be quite different from one another. And now we do the extreme case of like f10, this like function class that has polynomials of degree 10 or less. What you'll then find is that f star is basically f base, which is the answering the question is, yeah, you make this function class bigger, then f star gets really, really close to f base. It really becomes the best possible thing. Okay. But now what you'll find is that these f hats based on the data are extremely different from one another. So you get like one data set, you get this function, right? Look at the orange f hat. You get a different data set, you get something that's like not even close to this orange guy, and so on. If you change so if you get these really complicated, so as the function class grows, you're going to get these like very kind of like contorted functions that fit the data, but they like as soon as you change the data set to anything else, then the thing is going to be quite different. Okay, so this idea is called like overfitting, and maybe suitably so because it like overfits this data. Okay, so there's the main things once again to maybe point out is there's this f base, which is the best thing we could ever hope for, assuming the function class is as big as you wanted. This is the best fit. F star is the best fit if you knew like the true data distribution, but you were restricted to the function class that you're actually working with. And then these f hats are now the best fit if you have to use data instead of the true distribution, and you're restricted in the function class. Okay. So yeah, so these are some useful things to note. And what this will allow us to do now is to reason about what we should pick as f. Okay. And to do this reasoning, I write out a little bit more mathematically rigorously these errors that we have. And then I plot how this error changes as a function of this. So we're going to have this guy kind of on the x-axis, and we're going to see what the story is. And this is like a very important plot in machine learning. Okay. And someone's asking, so like we can say that the lines which intersect f hat, f, and f base have the most suitable value we want. Okay, I don't think I understand this question. So for the sake of time, I'm just gonna move on. Maybe you ask on Piazza. So yes, so there is on the right. I've just written out the three definitions I've had before: f base, f star, and f hat, and they're kind of in order of like the best to worst, right? And we have our actual predictor, okay? And yes, and in here we're just using f as like some general function class. It's not just f1 now. Okay. And here is the thing that I really wanted to write down, and it looks like we're actually quite great on time here, which is, remember this is the thing that we want to minimize. This is what was in the objective. Oh, okay. One thing just to make like notation make more sense and things, I'm like, okay, I write this and then I erase it just to make it even more clear. So this is the thing we had in our this is the objective we wanted to make small, right? It was the expected loss of our learner's predictor, like the predictor the learner outputs on average over data sets. This thing is like kind of annoying to write around everywhere, and it's like it hides the fact that this thing outputs a predictor maybe and stuff. So I use the more maybe nicer and convenient notation that I have above here, which is I actually plug in f hat, which is the thing it outputs, and I write this like subscript here to make clear that this is still a random variable of the data. So as data changes, f hat changes. Okay, so we're gonna do that. So and I'm gonna write it in orange because I'm gonna have colors for plotting in a second. Okay, so we want to know what is the expected value of this guy here as the data set changes. And it turns out that it's useful to write this out into some error terms. And the way you write these error terms is you do this. So you take this guy, And then this is a very classic kind of trick in maybe a lot of math, like more theory world of things, is then you add and subtract the things you want to compare with. Okay, so in particular, I would like to first compare to this thing that's like the closest to my f hat, so f star. So what I do is, okay, I then compare to the expected loss, right? The expected loss of f star, right? This has some error, plus this thing. So all I've done here is I've added and subtracted the same exact thing. But now I can think about how much error there is in this comparison. And then there's some inherent like error in how good just f star is. And then it turns out I can add one more term, which is to compare f star to f base. And this asks how close is f star to f base in terms of its estimate. And then I add this back. Okay. So this turns out to be a very it's a very classic way to decompose and think about how something breaks up into different error terms. And these have special names. And this is kind of the non-conventional thing that I said about introducing these error things in intro to machine learning. Usually this is like, you think about these error terms in a more, I don't know, advanced machine learning course for some reason. But we think about it here because I think it's way more natural. And then I tell you about the bias variance thing, which is the more classic thing you'll hear. And I think this is much more intuitive. So we're doing it this way. Okay, so these error terms are called the estimation error. And I will denote this as EE. This thing is called the approximation error. And these names have they're quite suitable for what they represent, actually. And this thing turns out to be called the irreducible error. Okay. So the names kind of actually explain exactly what's happening. This is like the best you could ever hope to do, given like what your features represent and stuff, called the irreducible error. This thing is how good like f star is at basically approximating f base. And you think of approximation in terms of how good does the best function in here approximate the best function in the set of all functions. And then finally, this estimation error has to do with how good is f hat, right, which is an estimate of f star in some sense. So this is this error. These are these like three things, and we can talk about how their corresponding basically losses compare. And I think I have enough time to say one more thing, which is like, yeah, I just said it in English, but I tell you this, and then we recap next class, which is the irreducible error is due to the inherent noise in the labels, basically. It's like you just couldn't do anything because there's just, for some house price, there's just, for some number of rooms, there's just a variety of different house prices you can expect. Like you're not just always going to get the same house price. The approximation error is really due to the function class being too small, while the estimation error is due to the randomness in your data set. Okay, and so we're going to talk about what factors affect each one of these and how do I find kind of the optimal, like, happy medium ground to pick. Okay, so that's where we end today, and we continue tomorrow or Thursday. Thank you.